All right, everyone, we're going to get started. Welcome to the HAI Research Seminar. I'm Vanessa Parley. I'm Director of Research Programs here at HAI, and I'm thrilled to introduce our speaker, Judith Fan, today. Judy is an assistant professor of psychology and directs the Cognitive Tools Lab at Stanford, which aims to reverse engineer the human cognitive toolkit and in particular, how people use physical representations of thought to learn, communicate, and solve problems. The lab uses a combination of approaches from cognitive science, computational neuroscience, and artificial intelligence. So in today's seminar, Judy's focus is on the lab's recent work on cognitive tools for uncovering useful abstractions. The talk will cover emerging research on how humans perceive, use, and accelerate their ability to communicate useful abstractions, and will close by noting the implications of embracing such behavior for advancing theories of human cognition and real-world impact, including AI and education. Before we begin, a few logistics. So for the folks on Zoom, you can use the Zoom chat to talk amongst yourselves, but please use the link that will be messaged shortly to ask questions in the Slido app. The Slido has that upvote feature so that I can choose questions that people are most interested in. And we will split the Q&A time for folks who put questions into Slido and then also folks in the room. All right, let's begin. Thank you.
All right. Oh, good. Okay, this is definitely on. It's great to be here. Thank you so much for the invitation to be part of the HAI Research Seminar Series. And also to all of you who are here in the room for coming out here in the rain. I am a computational cognitive scientist. So I'm someone who works at the intersection between human intelligence and artificial intelligence. And so one of my main goals today here as part of this HAI event is to share with you why anyone interested in developing AI should really care about human cognition, how we perceive and understand the world around us and communicate with others, especially if we do care about developing AI that's robust and safe enough to inhabit a human world. I'm going to start my talk by revisiting an observation that the architect Antoni Gaudí once made, that there are no straight lines or sharp corners in nature. And yet somehow we can all look at these axes here and not be totally flabbergasted. And yet pictures like these were actually cutting-edge tools of thought for driving mathematical discoveries not that long ago, when René Descartes and his contemporaries realized that you could use rectangular coordinates to link up algebraic equations and geometric curves to solve mathematical puzzles that has stumped the world for thousands of years. It would be impossible to overstate the impact of that central insight and that innovation over the last few centuries. This new tool converted all kinds of problems like these, where you might want to find out the set of values that satisfies two equations, into problems that rely instead on locating points of intersection between two curves. And this was a huge deal. It was useful, it was instrumental even in confronting major challenges in astronomy, optics, navigation in that time, but also for setting the stage for the invention of calculus. Without calculus, we really wouldn't have the modern world as we know it. We wouldn't be sending telescopes into orbit, we wouldn't have GPS, no microwaves, no television, no ultrasound, no telephones. Now, if staring at equations like these remind you of middle school and high school math class, maybe we just take a moment to marvel again at that fact. How did we get here where an idea that was actually revolutionary in the 1600s became literally elementary today? I think the story begins at least some 30 to 80,000 years ago, when anatomically modern human beings began to mark up their physical environments. So in this iconic example, these cave walls essentially repurposing objects and surfaces and their surroundings into carriers of meaning. And so each of these iconic images from the history of science captured some new way of looking at and understanding the world. So in the case of Darwin's finches, that beak variation might be related in some important way to a bird's ecological niche, setting the stage for theories of natural selection. Or in the case of Galileo's drawings of Jupiter's moons, the possibility that the solar system might be organized in a very different way than was acceptable to believe in his time. Ramon y Cajal's much celebrated drawings, certainly in neuroscience, exposing the detailed structure of the retina, and Feynman diagrams, opening our eyes to how subatomic particles wink in and out of existence and interact with one another, even if we may never directly observe them doing so. Now, notice that some of these images up here are quite detailed, others are much more schematic. Yet what all of these different examples share in common is that they leverage visual abstraction in various ways to communicate what we see and know in a format that's useful for understanding some aspect of how the world is and how it works. And more than any other species, we have leveraged that ever-growing understanding of how the world works to go and create new things. For example, our detailed understanding of physical mechanics allowed us then to go and design and build high-precision timekeeping devices. Much of this technological progress has been driven by our human ability to continually reformulate our understanding of the world in terms of those useful abstractions that make it possible to re-engineer the world according to our design. Translating, for example, biological insights into bioengineering, physical theory into advanced physical instruments, neuroscience into medical technology, and quantum mechanics into modern electronics. So what is it about the human mind that makes these feats possible? So here's a diagram that I've been using to help me keep track of the various entities and phenomena in play. And this is one way of illustrating the standard operating procedure in my home discipline, cognitive psychology, where the focus is on how individuals process information supplied by the external world. Here's how that picture is enriched by the study of social cognition, where we now consider the behavior of multiple individuals at once and how they interact with each other. It's a long tradition in cognitive science of noticing how when these activities are used to learn about the world and share that knowledge with others, that those activities share important similarities with formal science, even when they're pursued by non-experts in everyday contexts. However, I realize that the traditional mode in cognitive science still leaves out two key components, ones that I think we'd need to understand how humanity got here and where we're going next. The first is an account of cognitive tools or cognitive technologies, essentially material objects that encode information intended to have an impact on our minds, how and what we think. And the second ingredient is science's natural complement, engineering. How people leverage their understanding of the world, whether that's through direct experience or socially mediated, to create new and useful things. Because without a serious consideration of the engineering half of this picture, you'll never be able to explain how and why the world as we know it came to be. So at its core, research in my lab aims to close this loop, to develop formal cognitive theories that explain how we discover useful abstractions, that explain how the world works, that's the science half of this picture, jointly with theories that explain how we apply those abstractions to then go and remake the world, the engineering side. And the core hypothesis is that even the fanciest of our cognitive technologies that we've invented over the millennia, whether we're using a stone tablet or modern computing systems, accelerated by GPUs, are at the end of the day grounded in the need to coordinate visual and motor behaviors in the service of concrete behavioral goals, such as communication with other people. And thus our challenge is to develop a theory of how such alignment can be achieved between the contents of our perceptual experiences, the actions we can perform, and expectations about what other people will understand. And today I'd like to propose that such alignment relies upon what I've been calling bridging abstractions, so called because they're the core representations that lie at the crossroads between sensory processing and action selection and motor execution. And in the context of trying to account for how people produce, for instance, meaningful images and text, the form that these bridging abstractions take is assumed to be constrained primarily by a communication goal. In other words, to make sense. So here are the top level questions I aim to address in this talk. First, what are bridging abstractions and why are they important? What characterizes the abstractions that people create? And why do these abstractions take the form that they do? My plan is to offer a high-level overview of two ongoing lines of work digging into the kind of inherently multimodal and generative behaviors that we've been studying to learn about these bridging abstractions. So first is the use of visual abstraction to create meaningful drawings. And second, the use of linguistic abstraction to convey how objects are structured. So what makes visual abstraction such a useful domain for our purposes is that it naturally relies on three behaviors that build successively on one another. First, visual perception. So the problem of how we transform raw visual inputs into semantically meaningful perceptual experiences. And that in turn makes it possible to contemplate visual production, the ability to generate a set of markings that leave a meaningful and durable trace in the external world that has an impact on other people. Those two faculties then come together during visual communication. How we make decisions about what kinds of marks to make and how to arrange them and in what order in order to have an impact on other people's minds, to inform them, to teach, persuade, collaborate, or any of a variety of other communicative goals that we might have. So to get off the ground with the perceptual question, we started by considering the most concrete and familiar use case for drawn images, creating a picture that looks like an object in the world. The question is, what makes it so easy to tell the drawing here on the left is meant to correspond to the realistic bird image on the right? There have been two dominant ways of thinking about this problem of pictorial meaning. The first is that we see drawings as meaningful because drawings simply resemble objects in the world. Like this drawing literally looks like the bird, and that's how we know. The second is that drawings denote objects as a matter of convention. And we only learn which drawings go with which objects from other people. If you take this Chinese character, for example. So in an earlier line of work, my colleague Dan Yeamans, Nick Turk-Brown, and I discovered that general purpose vision algorithms, in this case, neural networks that can compose multiple layers of learnable spatial convolutions, were capable of providing a quite compelling basis for explaining how and why we perceive even quite sparse line drawings, simple sketches, as looking like real objects. But of course, that's not the whole story. A static, deterministic account of visual processing alone falls short of explaining how we generate and make sense of whiteboard drawings like these. What these blobs and boxes and squiggles mean depends on what we're talking about. So our next goal was to figure out how to incorporate that information about social context to begin to account for the sheer variety of graphical representations that we humans in fact use to communicate, ranging from more faithful pictures like those on the left-hand side of the screen to more obviously symbolic tokens like those on the right. In our first study tackling this issue, we asked how people knew when they needed to produce a more faithful drawing and when they could get away with something more abstract. So in that study, we paired people up to play a drawing game on the internet. The sketcher saw a display like this, where their goal was to draw the highlighted target object, and then we varied what the other objects were in this array. On what we called close trials, all the distractors, the other objects, belong to the same basic level category. So in this example, they were all birds, while on what we called far trials, the distractors were all from different categories. In using this really simple experimental manipulation, we discovered just how flexible ordinary people can be in the way they use pictures to communicate, making more detailed, faithful drawings on the close trials when they needed their drawing to uniquely identify a particular instance, but then sparser drawings on the far trials when they could get away with these category level abstractions. And here are just some examples of the different kinds of drawings that people made in these close and far contexts. Then to capture that behavioral pattern, explain it, my collaborators, Robert Hawkins, Mike Wu, and Noah Goodman, also here in psychology and computer science, and I proposed a computational model of the sketcher that used a convolutional neural network to encode visual inputs into a generically abstract feature space, and that was nested within a probabilistic model that inferred what kind of drawing to make depending on the context. Basically, a drawing that was detailed enough to help the other person, the viewer, know which object was the target, but no more detail than necessary. And while we were doing this work, the notion of bridging abstractions hadn't yet occurred to me, but you can think of this model implicitly having learned one in the course of needing to transform purely image-based representations into a format that could drive decisions about what kind of drawing to produce. I wish I had time to share the full details of all of the model ablation experiments here, so I'm not going to dissect this plot. But the take home was that both the capacity for visual abstraction, which we operationalized in that study as network layer index in our visual encoder, as well as a sensitivity to social context, were critical for capturing how humans manage to communicate about these objects at the appropriate level of abstraction. And in a more recent paper, now out in Nature Communications, we push this idea even further to understand not only the impact of the current context on how people communicate in visual form, but also the conditions under which new graphical conventions emerge. When memory for previous interactions with the same interlocutor, the same person, leads people to produce even more abstract, even proto-symbolic tokens over time, whose meaning depends increasingly on that shared context. Now, so far, just been focusing on drawings that convey information about object identity, but humans obviously possess much richer knowledge about the external world than just what things are called or what they look like. In a particularly important way in which we use visual abstraction, especially in science and engineering, is to transmit mechanistic knowledge about how things work. So what's going on in people's minds when they make that move, going beyond what's visually salient, let's say about a specific bird and what it looks like, to highlight underlying physical principles or mechanisms, like, for example, how a bird achieves flight. In recent work led by Holly Huey, a PhD student in my lab, and in collaboration with Karen Walker and Charles Liu, we found that when people produce visual explanations for a machine that they just learned about, rather than ordinary depictions meant to convey what an object looks like, that they reach for qualitatively new graphical elements, including, in this case, arrows to convey motion and causal interactions, even at the expense of preserving visual fidelity to the target object. So I'm not going to go into great detail in this talk. I'm happy to answer any questions about this. But the take home here is that however people are encoding information about how this novel machine here works that involves gears that turn in order to close a circuit and make a light turn on. They're getting that direct experience with the machine, and yet it's a clearly flexible enough mental representation of it that they can support really different readouts depending on what communicative goal they have, whether to explain or to show what the machine looks like. And altogether, what this line of work shows, it really doesn't seem to be a single set of bridging abstractions that are needed to explain visual communication, but rather the contents of this teal box in the middle can shift profoundly depending on a person's communicative goals and the context that they're in. But what are those bridging abstractions? What are they such that they can support that behavioral flexibility? Now, the technical approach that we took all the way back in ancient times in 2019 to capture contextual flexibility was limited in a bunch of really important ways, including its reliance on heavy supervision, its inability to capture internal structure within these drawings, also weak out-of-sample generalization. And the central problem, I think, is that we were ignoring this rich analogical structure that objects and sketches share. In other words, the pictures that people make of objects, in which the relations between parts of an object, for example, the spatial relations between the beak, body, wings, and feet of a bird, correspond in systematic ways to relations between parts of a sketch of that bird. In other words, that the units of action that people perform in producing a sketch, each stroke they laid down, are closely coupled to units of meaning, the parts of the object they think are relevant to include. So in ongoing work, we're aiming to more fully expose what those bridging abstractions are in this domain, which we think will mean developing and extending current advances in vision and machine learning, including self-supervised approaches to learning internal representations that carve up objects into parts that people find natural, thereby endowing it with the right kind of inductive biases to generalize to new visual tasks and data. Now, these very same goals have also spurred us to begin exploring our other major cognitive tool, written language. So in the last part of my talk, I'm going to highlight just one set of studies to give you a sense of our approach. The phenomenon we're after is how people use language to talk about what they see and want to do. For example, which objects are present in a scene, what parts those objects consist of, and even how to arrange those parts to create a new one. For example, if you're assembling a new piece of furniture at home. A remarkable feature of language is, of course, that it consists of individually meaningful tokens that can be combined in lots of different ways to achieve those communicative ends. Someone might, looking at these 3 best-selling nightstands from the IKEA catalog, talk about the small rectangular dresser with 2 drawers each, with 2 little circular knobs. But there's nothing in principle stopping that same person from reaching for entirely different words to talk about that same object, like the one with a 38 by 54 centimeter plank on top of the 68 by 38 centimeter plank, and so on. Or invoking its unique product identifier. This is the actual product identifier. I looked it up. This is the one. So any object can be described in a huge number of different ways. So what determines why people favor descriptions at one level of abstraction or another? So in this work led by Leo Wang, Will McCarthy, and Gabe Grand, we propose that it might be useful to think of people as inferring from visual inputs a kind of mental graphics program containing commands that correspond to the specific visual elements in their construal of an object. For example, perhaps in this program, a dresser function is invoked that takes a few arguments, such as how many drawers it has, the types of knobs, and so on. the specific attributes that characterize this dresser. An appealing property of such a mental graphics program is that it becomes natural to then read out linguistic descriptions that reflect that structure, such as a 2-drawer dresser. But there's an infinite number of different graphics programs that could in principle render to the same image, and thus a quite rich hypothesis space of possible forms this bridging abstraction might take, ranging from representations that invoke low-level primitives like lines and rectangles to representations invoking object-level chunks. So we formalized this variation in abstraction in terms of a concept library that contains the elements that are mentally accessible to a person, and then hypothesized that this concept library would be constrained to be representationally efficient. To show you what I mean, let's consider a simplified 2D rendering of this nightstand. Here are 3 different part libraries that could be used to represent it. From the most compact on the left, with just 2 functions to draw lines and rotate them, if you can read that, to the most comprehensive library on the right, with those base functions, as well as some more complex functions, like ones that can draw an entire dresser with knobs, even a function that can be used to draw this specific object in one fell swoop, like IKEA Hemnes dresser. Then programs that you can write with those libraries will also be different. With the leftmost library, the programs are necessarily going to be very long, since you only have lines available. With the rightmost library, you could get away with a minimum length program that invokes just that one IKEA Hemnes dresser function. And then for the library of moderate complexity, in the middle here, you're looking at programs written at an intermediate level of description, of abstraction, and you might use a dresser function parameterized with arguments to tell you about its distinctive properties. What we hypothesized was that the composition of this mental concept library that best captured how people carve up these objects would depend on striking a balance between the overall size of the concept library and the length of programs needed to represent the structural motifs appearing in the different objects they encountered in this environment. So to test that idea, we procedurally generated 2,000 different objects. 1,000 of these looked like CAD drawings of objects from 4 different subclasses. The other 1,000 were these red and blue block towers, and these are just some examples. You get a sense of the kind of variation both within and between these different categories. And then we asked people to generate descriptions of several different objects from each of the categories that they thought would be detailed enough to allow someone else to then recreate the CAD drawing, or, as the case may be, recreate the block tower that they'd seen. Now, what I'm showing on the right-hand side of this slide is first the representational efficiency of different concept libraries, from the most compact to the most comprehensive, okay? What we generally found was that the libraries of intermediate complexity encoded objects most efficiently by balancing library size and program length. Now, as it turns out, not only were these libraries representationally efficient, we found this striking correspondence between the libraries that optimize representational efficiency with those that also happen to score highly on their ability to predict actual human language about those objects, which we measured by fitting a machine translation model to align tokens from these graphics programs to tokens of language that people generated. Now, note that this correspondence, this dark green line, looking the way it does, was not at all guaranteed, okay? What it suggests, though, is that people generally prefer decomposing objects into nameable parts that can be reused for many different objects from the category they're describing. And a key prediction of our hypothesis is that what kind of encoding is representationally efficient depends not only on the structure of any particular object, but also what attributes it shares with other objects that a person expects to encounter in that context. So in ongoing work, we're exploring how the concept libraries that are active in people's minds and thus manifest in their language varies between different contexts with different data distributions. For example, in a world populated only with dressers, you might get pretty far thinking just in terms of dressers and knobs. But if you're trying to generate useful descriptions for more of IKEA's diverse offerings, then you might justify activating a larger library of simpler concepts to capture all of the variation that you encounter. And moreover, even if the object distribution stays the same, the library we use to communicate might evolve over time as we establish more common ground with other people. So what learning mechanisms might account for that kind of in-context adaptation? In a recent study led by Will McCarthy and Robert Hawkins with key contributions from Haliang Wang and Cameron Holdaway, we tried to get at this question by, again, pairing people up to play a game. This time it was a building game. One person played the role of the architect and the other the builder. The architect could see the plans for the towers they were supposed to build, but couldn't place blocks. The builder, on the other hand, couldn't see the target scene they were trying to recreate, but was able to take actions in the environment and place blocks. So it was up to the architect to provide useful step-by-step assembly instructions, which they typed into a chat window, which the builder could then use to reconstruct the target scene. In this study, every target scene was structured hierarchically. Each scene contained 2 towers, each of which consisted of 4 blocks. And then to see how behavior changed as participants learned to collaborate better with each other, we repeated each scene multiple times. And what we found was that between the first and final building attempt, the language that architects used shifted to a higher level of abstraction, with references to individual blocks becoming less frequent, but references to entire towers, in this case, participants tended to give these towers names like C and L, emerging and becoming more frequent. And we modeled this learning behavior by combining 2 mechanisms as a proof of concept. The first mechanism is one that incrementally discovers recurring subroutines in the underlying graphics programs that were used to generate each scene across trials, and that mechanism augmented the concept library with new part concepts over time. The second is a mechanism for then coining new terms to refer, new terms in language to refer to those new part concepts. This convention information mechanism. We found that this conceptually simple combination of mechanisms yielded an architect agent that could reproduce key qualitative behavioral patterns, including the bias towards tower level abstractions over time. Okay, so I'm going to wrap up shortly, so we have plenty of time for questions and discussion. Today, I shared work explaining how people use visual and linguistic abstractions in a flexible way to communicate about the external world. The larger goal in digging into these multimodal generative behaviors is to understand how behavioral goals, such as communication, constrain the alignment between the contents of our perceptual experiences and the content conveyed by our communicative actions, our publicly observable actions, giving rise to a set of what I've been calling bridging abstractions that serve to link perception to action. And returning to the questions that I posed at the outset, first, well, bridging abstractions are composable representations that are important because they support flexible multimodal behavior. Second, they're useful not because they're static, but because they can be modulated systematically and on the fly according to what an agent's trying to accomplish. And they can emerge even over quite brief timescales in humans. And third, evidence from our modeling work suggests that these abstractions take the form they do because they provide useful ways of reformatting or refactoring our experiences and plans in a way that's efficient for thinking and communication. Zooming out, what's the end goal here? So the mission really is to develop psychological theories, cognitive theories of what kinds of abstraction layers humans find useful. Because I think they will help to explain why our current cognitive toolkit takes the form that it does and what future technologies might work even better. And I think there are major opportunities to imagine tighter links between the kind of innovation that technologists here engage in, pushing the frontier of how technologies can augment our ability to think and how we collaborate with others, be they machine or like machine agents or other people. And tightening these links matter because when I think of the real difference maker for human intelligence, it's technology. We're not that anatomically different from our forebears from 30,000 years ago. What's new are all of the ideas and tools that we've invented along the way, including writing systems, mathematical notation, and modern data visualization, just to name a few examples. And understanding how those tools work and how to make them better matters, because these tools are at the heart of two of the most societally impactful and generative activities that we engage in today. Education, the institution, and the expectation that each generation of human learners should be able to stand on the shoulders of the last and see further, and design and innovation, the suite of activities and habits of mind that enable humans to continually reimagine a different world and then go and build it. So thank you all for listening and being here today. I'd like to acknowledge again all of the amazing collaborators who contributed to the work in this talk, our funding sources, HAI, and you all for listening. And I'm happy to take any questions. Thank you.
All right, thank you, Judy. We'll do an audience question first.
I just wanted to take issue with the first quotation that you showed. Since the nervous system, the cells take 1 to 2 milliseconds to refresh after passing their information on to the next neuron or nerve cell, then actually we're not looking at the world digital analog, but it's actually translated into a digital form, which tells me that we need some sort of model in our brains in order to be understanding the world. So I just wanted to make that statement.
Okay, so to play back and make sure I understand the issue you wanted to take with the original quote, and this is the Gaudi quote? Wow, cool. Okay, that's a real throwback. So as a reminder, so we're looking at this statement here, which is that if you look out in the world, you don't see the kinds of constructs that appear in like Euclid's geometry, right? This is like what I believe this is referring to, right? We're not looking like these are geometric abstractions that humans created. Okay, so that's a statement of that's one kind of statement about the world, okay? That these are, okay. And then there's another observation about neural computation and how individual neurons encode information and produce spiking patterns that are digital in some sense because neurons have to reach threshold in order to function. And a reflection on analog and digital ways of understanding various neural and cognitive phenomena. And I think it's a fascinating question, what the right units are for thinking about theories about cognition and neural computation. I think it could be very likely that theories that explain individual units in real brains may look very different from the kinds of theories that are really explanatory for the kind of emergent phenomena that I focused on in today's talk. But I think it's like it would be an interesting conversation to have in following up. Thanks.
I'm going to do one question from online. This is from Alberto Tono, one of our PhD students. What cognitive tools enable the distinction between form aesthetics and function math in design workflows?
Sorry, I'm trying to parse the question. So the question is, what
cognitive tools?
What cognitive tools enable the distinction between form and function in design workflows? Okay, let me now try to infer where that question might be coming from. I suppose so suppose Alberto, we imagine, okay, okay, so I am a designer, I am trying to create something new, maybe one of these nightstands or something like that. And as I'm doing so, I am working with prototypes, maybe some sketches of possible forms this nightstand might take. And I can convey I can propose different hypothetical geometries, like different shapes of the components of this nightstand pretty decently with pen and paper, but then maybe at some point and decide to move into a computer-aided design environment, which also prioritizes shape and geometry. And so it seems like in a lot of ways, many of the kinds of software, like computer-based systems, as well as non-computer-based systems, really support exploration of that space. But also there's, something that is clearly very important in design problem solving, which is other properties of that object, including the materials used to make it, or the surface texture. And then for that, you may really want other tools available to you. You might want a design environment, right, or software that makes it really easy to quickly explore the space of possible surface textures and materials and know what the consequences of those choices might be. And insofar as those are bottlenecks in current design workflows, you would want to intervene on those bottlenecks to make those design workflows work more smoothly. I suppose this is really a set of issues I'm very interested in, but don't work on formally in any way. So I don't know if that really gets at the place where that question is coming from, but
So next time we see it. All right.
Hi, I'm Natalie. Very nice lecture. Thank you so much. I've got two questions. The first one is, have you looked at the effect of the emotional state of the people that communicate on their ability to mobilize these bridging abstractions? That was one question. And the other one, sorry, I can repeat. The other one is, it's similar to the first, but the cases, the examples you gave were all about sort of instrumental communication. We want to do something together. And I was thinking, have you looked at other types of communications, like, expressing love or reading poetry to somebody, which is not about, communicating instrumentally. So,
okay. No, I was going to ask you to unpack the first question, but I think you did with the second, which
I think so too, yeah.
Yeah, so I'm actually quite humbled by that question because I've studiously avoided construing our activities as studying art. I didn't mention that term for that reason, because I find it an enormously daunting task to begin to understand all the ways in which we create artifacts that communicate everything that goes beyond the kind of instrumental purposes that I focused on today, right? So I'll limit myself to just expressing that humility, although I obviously am deeply fascinated by those phenomena, because it is something that is remarkable and quintessentially human, that, if I may, visual art is not pretty pictures. It's not making pretty pictures, right? It's like an expression of something that's inside you that you have to get out, whatever form it takes. And that's not the same thing as making pretty pictures, however many you might make. I'll leave it at that for now. We can follow up. I really love the question.
All right, we'll go to another online. So how might we use AI cognitive tools to transform the way we teach and assess students?
Wow, I promise I didn't plant that. Yes, okay. So this is a real dream. And for those of you who are local, who also participated in the AI in Education Summit that HAI co-sponsored last week.
Soon.
Sorry?
Be online.
It'll be online soon. No one's, we're confident it will be. we spent the day really thinking about that question. And I learned so much from engaging with everyone who was there last week. I happened to share a dream at that event of leveraging advances in so-called multimodal AI systems, basically AI systems that can see, hear, and understand language in order to, in ways that are more human-like than they are today, so that they can they can serve as accurate models of human learning behavior as the foundation for the kinds of AI teaching assistants and tutors that we might one day incorporate into learning environments. And something that I shared then was some new findings that expose some fundamental gaps in between where we are today and where we would need to be in order to integrate those kinds of systems at the base of those teaching and tutoring platforms to support teaching and learning. I also think, similar extensions to assessment really rely on having strong, like a strong foundation built on like a detailed understanding of human mental processing. And so I think that what we've developed and what we've been working on developing is protocols to be able to tell when we're on the right track and when we're veering off doing that.
Thank you so much for doing and sharing. I would love to hear a few of your thoughts on the ways in which or whether modern tools, the ubiquity and ease of modern tooling may have affected or perhaps even harmed our ability to understand some of these and create some of these more abstract representations, to make it just a little bit more concrete and perhaps easier to see why I'm asking. So I collect antique textbooks from mechanical drafting classes. And I, enjoy the imagery therein because not only does it communicate things, but it has an art style that I happen to appreciate. And people don't make those kinds of drawings anymore because it's too easy to grab a digital camera and take a photograph. But the photograph is not as simple to understand to me. So I just wanted to hear where your mind goes.
We should talk some more.
I'd love that.
This is really fascinating. Yeah. So now it's hard to believe, but 8 years ago, I went to Indiana University in Bloomington to speak with some, I think, other members of your disciplinary community about that shift. The way in which manual drafting classes had once been seen as essential, as like building a foundation of like foundational skills for being able to approach really difficult design problems in civil engineering and mechanical engineering and many of these disciplines. And, I think it was then an open question and remains today, what the long run impacts of these shifts in our curriculum are. Like I internally vacillated between, on the one hand, really marveling at and missing the kind of expressivity and immediacy of some of these media, including being able to draft and work through ideas on paper using physical media. And at the same time, thinking that the other affordances of digital tooling can be enormously useful for like quickly modifying, copying, not only reproducing, but also extending. And like there are a lot of different affordances of working in digital. And the place where I've been landing each time I go here is basically like a detailed enough understanding of what's going on between us, the pen and the page, the pencil and the page would give us the kind of insights that we need in order to make the other newly emerging tools work better, to provide those functions. One example that was really salient in that earlier conversation that I'm alluding to from 8 years ago, that I thought was really interesting, is like the role that ambiguity plays early on in the design process. There have been lots of people who have written a lot more about this than I have, and I'm trying to channel their perspective here and observing that there's often this like initial divergent set of processes where many ideas are generated, and that can be extremely useful for discovering solutions that aren't obvious or apparent at the outset. And then there is a stage of like pruning and selecting among these different design possibilities. But if you're beginning with a digital tool that, well, accelerates that process perhaps more quickly than the human designer is able to adapt and respond to it, it can constrain how expressive that human designer and maybe their contemporaries might be. I would love to figure out ways of measuring that, being able to track that over time. I mean, I think that, a lot of these questions remain unanswered, and they also sit, they sit really at the intersection between so many different fields. And so they're like quite challenging questions from like a structural standpoint to confront, but I think they're very important, especially as, design workflows continue to evolve, right? Even last year. So thanks for the question.
Audience questions in our in-person audience? Oh, yeah, all the way back in the purplish sweater.
Hey, Judy.
Hi.
Thanks for the talk. You talked a lot about like how different abstractions get used, and also like, like what is an efficient abstraction. I thought that was really interesting. How effectively there's a trade-off between like, how abstract the library is and how abstract typical programs can be. I'm curious, like what are the state of the art understanding of how people come up with those abstractions? It seems like humans have a fundamental, very low level tool set of like the things that they could do. You could draw, you could speak, you could move around in a certain way. And in the face of some kind of context where we want to communicate something, it almost seems like it's a very unclear process to me how we come up with those. Do we enumerate different possibilities and then kind of like, test it out in our minds? Or do we have like a rule, a set of things that we typically do and then we customize it? Like, I don't know, what is the conventional view on these things these days?
Thanks for the question. Your instincts seem right on the money here. I mean, I feel as if you're recapitulating many of the debates around this phenomenon in developmental science, the study of like cognitive development and thinking about like how it is that we end up learning the concepts that we do. Human babies do not trawl through web scale text corpora to understand what the world cares about. Nor does it seem to, nor do human babies train on the kind of image data sets that most modern vision algorithms use. And I think some of the most promising ideas at the intersection of cognitive science, especially cognitive development, and building artificial learning systems is really taking seriously that the kinds of constraints. I mean, this relates to this bridging abstraction idea, which is like the constraints supplied by being like an embodied agent embedded in the world, surrounded by other people who want things and need things and do things for whatever reason. Maybe not so transparently instrumental as they are in our laboratory tasks, but in general, that the way that people move around in very intentional ways provides a lot of useful sets of constraints on the kinds of abstractions that end up emerging really early on in life. That it's not just vision or language, but there's a bunch of other cues, right? Like how people are moving and other kinds of sensory cues and social cues that are really important for supplying those. So I hope that's like a partial response to your question, but the idea that like one proposal that you might be like enumerating all the different possibilities and then rejecting ones, like that is a proposal that has been in the field. Different researchers are working out what kind of evidence you might need in order to reject that kind of, or to test those kinds of proposals against these more like statistical learning approaches that are cross-modal.
All right, we'll do our most popular online question. This is from Ryan. He says, is it possible for AI systems to evolve intuitive decision-making? If so, what are the necessary foundational conditions?
This one too.
Yeah.
Is it possible for AI systems to evolve intuitive decision-making? If so, what are the necessary foundational conditions? Okay, so there are a few different constructs here that I wish I understood. But I'm going to try, okay, to make some guesses, and then we'll see where we end up. So to evolve, okay, so that could mean like something other than gradient-based optimization, or it could just mean that, but just using a different word. Intuitive decision-making. Wow, what's that? Yeah, so we call those things intuitions, basically, the things that we do understand, right? And so intuitive, I take it to mean like the kinds of like insights or steps in the chain of thought or feeling that are not directly penetrable to conscious awareness, that we may not be explicitly aware of, and nevertheless, we're biased towards certain kinds of judgments or construals of a situation or certain kinds of actions. And, you know, that kind of implicit cognitive activity does seem quite pervasive in human cognition, certainly. And so, you know, insofar as biologically grounded material processes evolved us, I see no reason why it can't emerge in another kind of system, whatever its substrate. What are its necessary foundational conditions? Oh gosh, we should just follow up afterwards. That's too big.
I really appreciate how you break down and these questions.
It's just like
very impressive. Yeah.
Like to see where they're coming from.
All right, we'll do maybe one or two more questions. So one more from the audience. Anyone has a final question?
Oh, hi, thanks for the talk. Are these cognitive tools culturally dependent?
Yes,
Okay.
that's like a whole thing.
Okay, then can you elaborate a bit more on?
Wait, sorry. That was uncooperative of me. My bad. Could you unpack your question, like as opposed to what?
As opposed to they are more universal and every human being learns in the same way.
Okay, meaning so, right. So this is really interesting. So you know, I just happened to be on this slide because we opened with it with this quote, by contemplating this quote yet again. So like the number line. The number line emerged in a particular place and time. It was popularized by people, spread throughout the world, and therefore through cultural learning processes, and therefore must be culturally mediated. It is not a thing that like an individual human spontaneous is very likely, it's vanishingly, the probability that an individual human comes up with this on their own within their lifetime is vanishingly small, okay? But the likelihood that you will pick up on what this is and what it means if you go to school is very high, very reliable. In that sense, it's deeply culturally mediated. Now, of course, different groups of people arrived at different solutions to the problem of thinking about number and counting and ways of keeping track of those concepts. And that is really important variability that would be really important to explain if we were to further develop this theory of cognitive technologies and tools. You want to both explain the systematicity that's shared, like the ability for people anywhere, if they go to school, to learn how to read the number line, how to use it to add and subtract and reason mathematically. And also the fact that this is not the only solution to the problem of reasoning about number or quantity. And so that's like one way in.
Okay, thank you.
Right. So we'll do one last question. This is from online. Again, a very popular question. Isn't language a tool that is created to express abstract minds? When talking about abstractions expressed by language, aren't there two layers then of abstractions?
Yeah, can I reread it again? Because it helps me. Yes. Oh, yes, right. Isn't language a tool that is created to express abstract minds or thoughts? When talking about abstractions expressed in language, aren't there two layers of abstractions? You've got this.
It as the language is itself an abstraction.
Oh yeah, yeah. Yep, I'm down with that. I'm down with that entire way of thinking about language, basically. It's like, they are. It's an extremely, like, it's very useful. Clearly, we're using it right now. But it's also like quite bandwidth limited in all of these really interesting and important ways. Like, only say one word at a time, right? And the fact of that puts really important constraints on the form that language takes. And I guess the null hypothesis that I have is that many of those same deeper constraints that sculpted the form that language takes also sculpt the form that our external representations of thought take too. So like that's like my null. And then where there are exceptions and where, you know, pictures work differently or diagrams or maps or visualizations work differently and other kinds of media like differ from each other, I think those are really important, you know, those are also very important discoveries to make.
Okay.
Cool.
So that is all the time we have. We can stick around if you want to chat further. I don't think there's any more food in the back, but yeah, feel free to stick around. And thank you all for coming, especially in the rain. Hope to see you next time.
Thanks, everyone. This was fun.